The current from the battery gets divided into three parts when it encounters this parallel combination. I'll call the top current I1, the middle one I2, and then noticing that this bottom leg has the same resistance as the top one, 25 ohms, it must also be I1. And then the currents recombine to pass through the remaining two resistors. We're asked in Part A to determine what the voltmeter reads. Let's start by calculating V1, the voltage across that 25 ohm resistor in branch 1. It's the current through it times the resistance, which works out to 31¼ volts. The 15 ohm resistor beneath it is in parallel, so the voltage across it must be the same, which allows us to solve for the current I2. It's the voltage divided by the resistance for that middle branch in the parallel combination. And that works out to 2.08 amps. Now we can calculate the total current I in the circuit. It's the sum of the currents in each of those three parallel branches, the top, middle, and bottom, working out to 4.58 amps. If we now move on and look at the 45 ohm resistor, we can calculate the voltage across it. That's what the voltmeter reads, as the current through it times its resistance. That works out to 206 volts. Part B asks us for the battery's EMF. One way to solve this is using Kirchhoff's loop rule, which says that the sum of the voltages around a closed loop equals 0. If we start at the battery, we encounter three voltage drops. First across the parallel combination, then across the 45 ohm resistor, and then across the 35 ohm resistor. We know two of these voltage drops, and we can calculate the third as the current through the 35 ohm resistor times the resistance, finding that the battery EMF equals 397 volts.